Am I doing it? It seems so. Yes, it says interrompi me, which means we're doing it. Okay, great. I have to give my cell phone because there is somebody that is relying on me if something goes wrong. Okay, long story short, I have to keep it on. I am sorry. Okay. So let me say a little bit. Oh, sorry, I have to let in the people. Sorry about that. Ok, metti tutto. All right. Okay. Okay. So some remarks on loss remarks. So you don't mind if I do a little bit of, you know, this. I don't have the board, so I figured that was the best. Okay. Remark on the loss function and some information geometry. Okay. Because we just touched it and some people asked me about it. So when we're in deep learning, we are looking at the following loss function. So for one image, so the loss function depends on the data of the image right here. And this is the weights, right, of your neural net. Oh, sorry, weights. So for example, the image could be an element of, say, for example, for the mist is like 84, something like that. The weights is much more. Typically, you know, is in the order of the 10,000, something like that, okay? Perhaps more, perhaps less. This is roughly the order of magnitude. This is a scalar function. The definition in deep learning of this scalar function is, all right. Today we have more people. They don't know what they're in for because last time was all slides and fun. Now it's like mathematics, so they probably run away immediately. I like that. So this is minus the logarithm of E to the score of the image. Okay. I have to write it carefully. So let me, so there is a little X here. Okay. Summation J E to the Sj of X. So let me remind you this very ugly function, what it means. So you have an image X. For example, in NIST, you have like a number 2. So this image X will be subject to a score function, and the score function will output a list of 10 numbers. So this be 10 numbers. So these numbers, I don't know, like 12, I don't know, 144, 13. They're just numbers. Actually, there will be random numbers. Perhaps they have like, they're fractional, I don't care. But when you do the softmax function, you see if you do E to the Si, so that it will be a vector that has exactly 10 entries because it's the number of classes, right? And then when you do this divided by the sum, you transform it into a probability, meaning that you have this probability, xw, w are the parameters, and the sum of this pi is 1 by the very construction. Okay, so this is the perfect. Now, last time I was making some remarks about the theory of probability, which I know very little, and this loss function. And some people ask me, oh, how about the Kullback-Leibler? Nicola made a comment that kind of confuses me, but then immediately I thought, no, I was right, Nicola, you were also right, but I will explain. And then I want to put things in a context, okay?
Rita, may I ask a question?
This is called the cross entropy loss. That's the name. But there is something called the cross entropy in the theory of probability. So first of all, what is it? So there is something called the Shannon entropy of a probability, which is the following. You do the expectation value of some of minus the logarithm of a probability. So now you forgive me that now P is any, so this is more general, right? So what I'm writing here is more general than deep learning. So you can find something called the Shannon entropy. Okay, and this is the expectation value. What is it? You know that? You know that already? Yes, no? Good to review. Eh? Yesterday, not before yesterday. I hope so. Right. So what is
Rita,
okay? Then
can
let
you
me
hear me?
question the class. What is the Shannon entropy representing? No,
Rita,
because you made the claim, so I question. So I quiz to the class. No, okay. You guys have to know. I ask all these questions because I want to know where we are. I don't want to say obvious things to you. So what? No. If somebody is, oh, wait, they're having some chat thing. Ah. Turn on my speaker. Now you say it.
Rita,
Wait,
can you hear
you
me?
are correct. That is very sad.
Hello.
I am so sorry about this.
It's okay. It's okay.
All right.
Someone wants to ask a question.
Rita,
Yes.
may I ask a question?
Absolutely, yes.
In your first line, you define y x of x. What is it? Why?
But you have no patience. I was going to explain it, but okay, I will tell you now. So this yx, that is the correct label of x. Okay. So what do I mean with? I wanted to say it later, Cinzia. But
okay.
But since you asked, I will briefly say. So, for example, suppose your image is, I don't know, it is divided like that. So you get here some probability. I don't care what it is. But suppose your image, this noise is very. Suppose your input image is a cat. No, actually, we're doing NIST. So your input image is the number 2. Okay. So this is 0, 1, 2, and then 2 will be the label of the number. So if this is number 2 that has label 2, this is so y x is equal to 2. Now here is a particular coincidence that the number is also the, is an index, right? But suppose 2 is a cat, is assigned the label 2. Okay, so yx is that number that is associated to the image x, the true label. Is it clear? Cinzia?
A bit, not too much. Is a number associated to the image any number?
No. It's difficult to explain. Okay, so suppose I have I have categories. So I do an example that is not, so I have a category cat, that is a category 1. Then I have category dog, that is category 2. I have category horse, that is category 3. So I give I give labels. You understand?
Yes, I understand.
Okay, perfect. So now I give you an image. So my algorithm produces a probability. So the probability will be 0, 1, that is a cat, 0, 2, that it is a dog, and 0, 7, that it is a horse. Okay? Fine. So category 1, category 2, category 3. But the YY is category 1. So it is equal to 1, is the index of the true label. So if this image is the image of a cat, YX is 1, because the cat is associated to label 1. Clearer? Yes or no?
Why not 2 or 3?
Because we decide from the beginning that every time we have a cat, we say this is label 1. Every time we have a dog, we say this is label 2. And every time we have a horse, it is label 3. Okay. So great. It is a labeling, but it is very important that every image has a true label that is assigned to it. No, this is quite a remarkable point, because I'm going to make it in a moment, but I didn't want to make it now. That's why I was reluctant. So let's, for the moment, wait for this point, which is interesting, but wait. Look at Shannon entropy. So Shannon entropy has nothing to do with deep learning, labeling, nothing. You give me a probability, I give you this definition. In our case, for a finite, a discrete probability, this is by definition the summation of pi logarithm of pi. This is the definition, okay? I'm not doing anything smart. I define it like that. For a generic probability, not the deep learning any. Now, question for you guys. What does Shannon entropy measures?
It should measure the uncertainty related to a certain event or the information we could gain from a certain event.
Exactly. So in our special situation, you see that whenever the probability is a mass probability measure, so suppose that your probability is like that. Suppose that you have 1, 0, 0, okay? What is a Shannon entropy in this case? In this case, the Shannon entropy is 0 because you get three things: 1 times logarithm of 1 plus 0 times logarithm of 0, that we know that our friends, the computer science people, have no problem in writing, plus 0 times logarithm of 0. So this is equal to 0. Okay? So for a mass probability measure, this is 0. And this is somehow the probability measure, as you correctly were saying, has the most information because it tells you certainly this. Otherwise, if you have a very spread probability, the entropy is high because it will be all. I don't know, you that participated, were you going a similar to say similar thing, right? Perhaps not. Let's hope a probabilistic is not hidden in the audience. Somebody participated, but okay, not anymore. Okay, this is the Shannon entropy. Now here we have actually two different probability going on because we have our empirical probability. So we have a P depending on X and Y. This is the empirical one. This is how really it is called, empirical probability. Why empirical? Because we have our weights, we start random, God knows where we get, right? We don't know. And certainly it is not always correct because sometimes it's wrong. And then we have this Q of X, which is the true probability because we have a labeling on the image and we know if the image is a dog or a cat. So in the previous case, for example, in this example here, which I underline in yellow, what happens that we get the empirical probability for the three classes 0.1, 0.2, 0.7. And then we get the QX, so this is my P. The Q will be clearly 1, 0, 0, right? Which is quite different. So, Cinzia, I don't know if this clarified, because this is when I wanted to. So the YX remembers what is the true label of X.
Yeah, thank you.
Okay, no, I'm glad because this is an important point. So what we really care is not just the Shannon entropy. That is, okay, it's telling us information, but it's not telling us a whole deal of information. We care about what is called the cross entropy. That measures the difference between the true probability Q and the probability P, okay? So there is this other quantity, okay, which is minus the expected value according to the probability Q, which is the true probability of the logarithm of P. And if we write it, what do we find? We find minus a summation of Qi, in our case, in general, but let's write it in our case, and then the logarithm of Pi of XW. But let's write it more extensively. So if we write it more extensively, remember that when is it, so Qi, this is equal to 0 or 1, right? And it is equal to 1 only when the index I is equal to Yx, right? When the index of the probability, so this is your Yx in this case. So we obtain minus the logarithm. So if we substitute 1 of the probability, okay, perhaps I should do another I should do another, okay, should I do or not do? Key to the score J. Okay, summation over J, the score J, E. Here I should write S to the I, but then I is replaced by Yx. So we get really the loss, okay? So I'm trying to tell you that our loss function in deep learning is exactly measuring the cross entropy loss. The difference, not the difference, but measures the difference between the true probability, which is a mass probability, this is my Q of X, and the empirical probability that the algorithm is spitting out through the score. So perhaps last time with the slides, I think it was faster. It is better. Some people ask me for clarification. I don't know if you guys like more detail. I don't know. They asked me about it, and so I gave. Then the person that asked is not here, so I don't know what to say. Okay. Questions on this point? So this is called the cross entropy. That's why it is called cross entropy. Now, there was a question last time from Nicola regarding the Kullback-Leibler divergence. So let me put, so are there questions on this point? Sort of happiness? Okay. There was another question. I'm really glad when there are questions because so I know that I explain things that, because I'm always afraid to say obvious things, right? Because I don't know the audience. No, you say, I don't have this danger. Okay, whatever. All right. No, but you guys have to tell me. Okay, so last time Nicola asked me this question and we exchanged also mail. And he said, well, Kullback-Leibler divergence of two probabilities. What is the definition? Okay, because these are definitions, right? So definition of Kullback-Leibler is the following. You take, I'm always having discrete probability measures. So I do Qi. This is nothing to do with deep learning. This is really a definition. Qi mod Pi. That's a definition of Kullback-Leibler. Okay, great. But then you see, there is, since it is logarithm, we can write summation of Qi logarithm of Qi minus summation of Qi logarithm of Pi. Okay, what do we see? Well, we recognize there is the Shannon entropy, Hx, and then there is the plus, because this is a minus, plus the cross entropy. Okay. Now, you are very correct, Nicola. Last time you said the Kullback-Leibler is not equal to the cross entropy. This is true, not equal, but in our case, it is equal because we said that the Shannon entropy of the Q, sorry, I should put Q here, sorry about this. So the Shannon entropy of Q, it is equal to 0. Because that's is the thing I was writing here. When you have a probability mass type, then you have 1 in one spot, 0. Otherwise, this thing is 0. So,
Thank you, thank you. It's really clear now.
Nicola, right?
Yeah, thank you.
Yes. Yes, yes, no, but I wanted to say, because last time it was very fast. With the slides, it's okay. And this is also the loss. Okay, so this is the rate. Now, I just want to say, I said it last time, that this is what Amari called loss. I call it Amari loss, but he says the loss, which is very like a desperate thing, because you're calling loss something that in deep learning is not loss, but whatever, doesn't matter. Fine. And then I showed you last time, so there is some points I want to clarify also coming from last time regarding the Fisher matrix, because I want to say something more. So it wasn't you asking me, Philippe, about that? No. Okay, whatever. The other guy. Okay, whatever. All right. So the Fisher matrix is defined as a definition, is a matrix, is a symmetric matrix, is the expected value according to a certain probability of the gradient of the logarithm of p times the gradient of the logarithm of p transpose. So you get actually a matrix, because you think of the gradient as a vector. So if you go vector times the transpose, you see you have I don't know, it's like you do something like that. I show you what you're doing. You're doing something like this, right? V1, Vn, and then you multiply like U1, UN, you get a matrix of the type V1, U1, V1, U2, you understand? And then V2, U1, and so on, okay? This is why you get a matrix. You do this multiplication. And since you are multiplying identical vectors, it's symmetric. Very simple. Okay. You take the gradient with respect to the weights. Okay, this is the point. Now, I want to express a proposition which I only mentioned, which is extremely important in information geometry. and the people in deep learning somehow use and know, but the truth is that they don't, they don't state it appropriately. So the proposition is that the loss, which we know, it is the Kullback-Leibler divergence that we know. No, I don't want to say this. I want to say something different. No, it is related to the loss, but is not equal to the loss. The Kullback-Leibler divergence of P of X. This is equal 1/2. Okay. So we approximate the difference between probability in a point of the parameter space and the probability with a little variation with the Fisher, with that. Okay, why is this important? We are going to show it because it's very simple, it's very, so let's show it, and then I make some considerations. So we write what it is. So the Kullback-Leibler of P. So I forget the X, so to save space. So there is always X, but I forget. To save time, I don't write the X. So this is by definition the summation of PI W logarithm of PI W divided by PI W plus delta. Okay. So what we do, we write as before PI W logarithm of PIW, and then we subtract summation of PIW, and then I should write, well, let me write it, logarithm of PIW plus delta W. But now we use Taylor expansion. So if we expand with Taylor this, what do we get? So we get PIW plus the gradient of PI over PI. So it is, so you are doing the logarithm of something, right? With respect to many variables. So you have actually a vector, right? So you get, sorry, I forgot the delta W. Times delta W plus 1/2 delta W, the Hessian of the logarithm of PI delta W. I forget where is the transpose, is probably here. So you get to get a number, right? That's Taylor. All right. So you see immediately the following, that so here you have PIW logarithm. I tell you why I do this to you guys, because I tell you what the people do in reality. So, so I write, no, I made a mistake. This is logarithm of PI, sorry, logarithm of PIW plus, so this clearly goes away with this. Now what remains is minus minus 1/2 okay. Now we have a summation of the gradient of PI, but the gradient is, you know, it's linear, so we can move summation out. So we get minus gradient of the summation of the PI, which is 1. So the gradient is killing it. Minus 1/2 okay. Now, last time we proved that this is really the Fisher, okay? So this is actually minus the Fisher. This is something we proved the last time I was showing it. So we get our result, okay? There is plus or minus, that is probably is an error, but okay. So it's only, now what do you read? If you try to look for this result on the literature, of course they do it, but they do it with integrals because they don't get it that we are in discrete. It is true for this result is true for integrals, but why doing integrals? Sure. Yes. No, of course, I am very bad. You are very right. I am very bad. I forgot the summation. Very important, thank you. No, very important. Why very important? Because it's not true. No, but I am sleeping. It's not true. So the Fisher is the expected value of the Hessian, right? Not the, we saw this last time. Okay, so not that, very good. There must be the summation. It's, I forgot it, but it must be there. Thank you. It is very sad that we are recording, so everybody sees when I get confused. Okay, whatever. Okay, but let's, this is very good, but let's see what this thing says here. This yellow thing. So it says the following, that you are in the parameter space, you have a dynamics, because this dynamics is the stochastic gradient descent, right? So you're going down with this strange way, you know, at this delta. So this is this thing here in deep learning. This is W at time t plus 1 is W at time t minus learning rate. That is what it is, right? Is the update of the weights. Now, this is telling you that the distance, I know Kullback-Leibler, it's not a distance. We know that, right? But the distance between these two probabilities, it is it is approximated by this scalar product, because that's a scalar product with the Fisher, right? It's not Euclidean. There is this symmetric matrix, but that's a scalar product. So this Fisher is thought giving a metric to the space of parameters. But when is it giving a metric? When these two probabilities in one point, and they're very close to each other. So the algorithm is almost at the end of its training. Because clearly, if you start the algorithm by random weights, what happens? That, you know, you measure probability, then you move a little bit, the probabilities can change greatly. Actually, you're doing it in such a way, they must change greatly, because when you give me the weights randomly, they're all wrong, the probability. So you want them to be right, so they're going to change, right? So this yellow approximation will work only when you are close to equilibrium, when your loss is very small and you reach almost the optimal. Clearly, if you wait until the algorithm is over, this is going to be zero, because in the end, the probability doesn't change anymore. The algorithm is really sure. It says, you know, you give me the image X, that's going to be a cat. And if you move a little bit the parameter, it's going to still be a cat, right? So, so it will work almost at equilibrium, not at equilibrium, not far, but almost. Okay, this is, and there was actually a very nice graph due to Soatto that was showing the information content of the Fisher, and was showing that it was showing a graph like this. I write the graph, but I know it makes no sense. This is time, and it was showing the eigenvalues of the Fisher. The sum of the eigenvalues, they're all positive, okay? Perhaps I prove it, perhaps not. And so it was doing something like that. So at a very long time, it's going to zero. But you may, so it is right here that you are making this approximation when you're almost at equilibrium, but they're not at zero. So this is the idea. Now, the sad part of all of this is that they talk as F were a metric, but F, it's not a metric, because F is degenerate, okay? So it has a strong degeneracy, and this cannot be cured. So it's really very bad. And so the only hope you have is, so it's not a Riemannian geometry. So whenever you put a metric at a point, you have a metric, meaning you have a non-degenerate scalar product with all eigenvalues are non-zero, then you speak of a Riemannian geometry. But here is not, because the eigenvalues will go to zero, many of them. Okay, so this is the bad point. Any questions on this point? Because I wanted to say a little bit more about the geometry of this system, but I don't know. The people that ask me a geometry, they are not here.
I have a question, but I don't know if it makes sense. I was just wondering.
Who are you?
Nicola.
Nicola, go.
We know that Kullback-Leibler is not a distance, and I think, if I'm not mistaken, the property that doesn't hold is the one that if we have that the distance between two different probability measures is equal to zero, but we're not sure that these probability measures are equal to each other.
Yes.
Isn't it?
Yeah,
Okay.
something like that.
So,
yeah.
what if we have, if it happens in this case, so we have two probability measures that are really close to each other, but they're not the same clearly. So we can do this approximation with the Fisher matrix. What does that mean? It means that we can actually have a wrong result, but knowing that we are kind of approximating like with this, I have this doubt here when this thing happens. So I have two probability.
No, I understand your question. I really do not know the answer. I don't know.
Okay.
People, this is a very new thing. And the fact that if you go in the literature, they will show you integrals here. It shows that these people are not, so they're trying to borrow stuff from here and there without really understanding what's going on. What does an integral mean here? We have like 10 categories. That's a sum of 10 numbers. Why are you doing an integral? It's not even close to an integral summation, right? That shows to you how far these people are from what is happening.
Okay, thank you.
Okay. But coming to the question I received from the audience, so perhaps it is worth for me, I wasn't sure I was going to do this. I perhaps show to you the bound on the rank. Okay, so let me, so F is thought by many as a metric. Okay, so what does the word, but it is not, okay, so it is not in deep learning. So what is a metric? So the word metric means that to a point of your space, so you have a space of parameters, so let's give it of dimension, whatever, let's call it n, okay? So W, I am very bad. Why do I call it P? We said it's parameters. So we have parameters W. So this is a point in the parameter space. And we associate to this point the Fisher, okay? Which is the expected value of, according to P, of the logarithm. No, sorry, what am I doing? I'm thinking about the gradients. The gradients is the gradient of the probability times gradient transpose, okay? We associate. And since we are in Rn, when you have a metric, you are associating a scalar product on the tangent space. But we are in Rn, so the tangent space is Rn, right? So you can think of F, so metric from a point P in Rn, associate a scalar product on the tangent space in Rn, which in our case is Rn itself, right? It's here, the tangent space is flat, okay? And that's what people do. But you want this product to be non-degenerate, okay? That is very important. Otherwise, because you want to be able to compute the distance. Now here, it's not difficult. I'm going to show to you. Perhaps, yeah. I'm going to show to you that this in the deep learning, the rank of the scalar product, so the number of non-zero eigenvalues, it's very low. So you have parameters, 10,000 parameters. The rank is 10, it's very small. So you don't have a metric, and people consider it a metric. What does it mean? It means that when you have a metric, I can compute the distance between you and me, right? I can measure the distance. Perhaps it's a curved metric, right? Like on the Poincaré disk, it goes around. Or visualize a sphere. Yeah, it's like a curved thing on the sphere. But I still can measure distance. But if you have a degenerate metric, if me and you sit on an eigenspace of eigenvalue 0, we are coinciding and we're not. You see the problem, right? You have a degenerate metric, it's very bad, right? Because it's not a metric, it's... Now, before I give you I don't want to say a solution, but I give you an insight of what is going on, because we are still trying to figure it out fully. And we are throwing at it a lot of geometry, but I must confess that this thing is escaping. But have I answered your question? Okay. So let me make an observation, which is a very simple observation. So you're looking at the kernel of this metric, okay, at a point. So this kernel is coinciding with the span of the gradient of the PI, orthogonal. So you have your probability, right? So you have probability P, which is the empirical probability. So there'll be numbers here, 0, 1, 0, 2, whatsoever. So P1, P2, P10. And then clearly, we don't know if these gradients are linearly independent. We don't. But assume they're linearly independent. There is 10 of them. So they span at most a 10-dimensional space. Now, the gradient, you take it in, so remember that we are in R, very large, so N is whatever, 10,000. We know that in ResNet is like what, 1 million? I forget, it's very big, right? So in a very small network, perhaps is a few thousand, in big network is 1 million. So this is telling you that the kernel is something huge, because you have orthogonal of a 10-dimensional space, so it's 9,000. You understand, right? So this is big dimension. So small rank of FW. So the rank nullity theorem, right? Dimension of the rank plus the dimension of the kernel is the whole thing. So, I mean, it's very bad. Okay. So let me make you this little observation, because it's a toy observation. And then let me tell you a reflection on this. In fact, let's look at the transpose of a vector, Fu. So I don't write the parameter anymore. So this is U transpose, and then you do the expected gradient, I forget, gradient logarithm of PI. Transpose U. So what you have here is, so I write the summation PI, and then I do a multiplication. So it's, okay, UK del K. So I have to multiply vectors, and so the gradient is a vector. My vector U is also a vector, and this is, okay. What should I write? I should write something like this: U scalar product with the gradient of the logarithm of PI. This is it. This is UK del K logarithm of PI. Okay, just, and then I have to do the same thing here. So there'll be like U times this transpose, because I'm doing the transpose of that. So that would be U, that would be del J logarithm of PI times UJ. Is a multiplication rows by columns, but it becomes a scalar product. Now you see that this is the same quantity multiplied by itself. It's a very tiny observation. So this is summation of PI u times gradient of logarithm of pi squared. This quantity is positive or zero. Okay, why? Because the pi are probability. Probability is positive. So you are summing positive quantities. At most, perhaps is zero, but cannot be negative. Now, this fact will give me almost what I want. Why? Because now we prove that. So what do I do? So I prove kernel is contained in the orthogonal. So this is almost evident, right? Because okay, let me rewrite it better, because it's almost evident but not evident. So this is summation of pi u times the gradient over pi squared. Actually, even better. Sorry, I am bad. Bad professor, bad. I rewrite u. I just rewrite it in a better way. U times, oops. Oops, I cannot do it today. Okay. Okay, I didn't do anything, right? Still positive. Now, if you take an element that is in the kernel, so if u in the kernel of f, this implies that fu is equal to 0, but also that u transpose fu is 0. Obviously, if it is 0, multiply, it is 0. But this implies that this guy here is 0. Because this was this, right? And I have a sum of positive quantities. They are 0 only if they're all 0. You don't seem convinced. This is positive, right? Oops. This is positive or 0. So you have a positive quantity divided by positive. And I'm saying this must be 0. Well, it is 0 if every term is 0. That's the thing. So this tells you that u must be 0 for all I. Now the vice versa is very similar, because so now you show that the kernel of f contains the span. There is a purpose to this, because there are some geometers among us that are listening to me, and I'm talking to them especially. So how to prove the other way around? So suppose that u times pi is 0, right? So this means in particular that if you do, so if I take fu, this is the expected value but this is expected value of gradient of the logarithm of p times u times and this is 0. So this is 0. Okay. What does this, do we understand this proof? So this proof says that, hence, we prove that the kernel of f is equal to the span, or if you prefer, that the rank of f not that the rank of S is bound by the number of classes. Okay, what it means. This is equivalent. Is the rank nullity theorem. But looking, okay, do we understand this point? Because I want to make some deeper geometric considerations on this system that are keeping me at bay at the moment. And I'm thinking about this every time, every day, and I cannot, okay. So if we're looking, so I want to make so you guys that are following us, so those that are still not asleep, do you have comments on this important point before I go and make more abstract considerations? No questions? Okay. Now, if you take a point in your parameter space and you associate it to a distribution, okay, forget I said the word distribution. You associate it to a subspace, which is the span of delta P1. This is called in mathematics a distribution, but that's not important, what is called, right? So at each point, you have a linear subspace, which is the span of the gradient of the probability. Clearly, it is generated by C, for example, is 10, right? For the NIST is 10, for CIFAR is 10, maybe so it's a small subspace, perhaps has dimension less, of course, if they're dependent. They're certainly dependent for whatever. I don't want to get into how much they are linearly dependent or independent, but this is at most 10. Our only hope is that we could see if F restricted to this tangent space, this W, is non-degenerate, okay? This is a hope that is non-degenerate. The problem is that you wish that there is some submanifold on which this is the tangent space. Now, in mathematics, I know you guys are not like abstract mathematician, but there is a theorem called the Frobenius theorem that gives us really like a criterion to decide whether or not this distribution, this linear space is tangent. For example, if you have a circle, you see, you look at, if you look at for example, if you look at this linear space, even a child can tell you, yes, this is there are circles that are tangent to it at each point. But if you give me random things, maybe not. So it is, Frobenius theorem is a criterion, which I don't go into it. Sadly, F does not satisfy Frobenius theorem criterion. So F will not be a metric on any submanifold. So this is one way out that no, cannot be used. There is another way out, sub-Riemannian geometry. So I spend just 1 minute. On the opposite side of Frobenius theorem, there is the so-called sub-Riemannian geometry. I will say a little today about it. What is a sub-Riemannian geometry? Is when you have a differential constraint like you do here, because there is this metric F, the rank is giving you a subspace. There is no manifold, but the gradient behave in such a way that they generate the whole space. So if you take, you know what a bracket is? No, you don't know bracket. Okay, don't worry. There is a criterion. But no, it is not even sub-Riemannian geometry. So I'm just telling you that as a geometer, there are some way out to this situation, but the usual way out is not working. So we need new geometry. What is available will not give us the geometry of this space. There is no submanifold, like for example, the nice sphere you go around, no. There is no sub-Riemannian geometry, whatever, you don't know what it is, see, you are lucky because you don't use it, so you don't need to know. So this is, we need new geometry, and the worst of all is not even a constant rank. So what happens is that this distribution will change rank depending on when you are, where you are. So the rank of the Fisher is not 10, can be up to 10, but can be 2, 3, 4, whatever in the point you are. So I've been speculating on the significance of the rank of this Fisher because I've been thinking. Because, so let me, do you have a question on this point? Because I want to make another crazy observation on things which I don't know. Yes. The number of classes. For example, 10, yes.
There is no pause.
Less. Maybe I said more because today is a bad day. No, it's my fault. Certainly I said the wrong thing, but of course the rank nullity theorem tells us that is up to 10, not more. Yes, Cinzia, you were asking something?
There is no pause in this lesson, or no break?
I'm going to make a break when I say my next crazy observation.
Okay.
Because then I will leave this, I will stop presently, just give me a moment. You can repeat all of this and define F for the data. So you could pretend that instead of the parameters, you have data. For data, the distribution is good, meaning it is used, you can use Frobenius theorem. So there is a submanifold of data. It's called involutive, whatever that means, don't worry about that. But the rank is still not constant. So it is involutive, but so it is, again, a challenging question. What I find it extremely fascinating, this is my remark, then I will stop, is the following, that the rank of the Fisher will change depending on where you are. But when you are at a point of the data, because see, the data is scattered, right? If you go in the space of the data, so if you are in NIST, you are in R 784, right? So you're in a very big space. And your Fisher is applied to this context is different rank, up to 10, but can have 5, 8, never reaches 10, but 2, 3. What we found very fascinating with my student Elliot is the following, that if you put yourself in a point of the data, you see, because if you are in this space, not every point is a data. Actually, if you pick any element of R 784, is probably white noise, right? It's ugly. Only some points are numbers. Now, if you go on a data point, so if you go and compute the rank on a data point, you see the rank is 2. It's very interesting. Why 2? And we find it fascinating, the fact that if you go to the number 1, the rank is 2. And actually, you see that the 2 gradients that are meaningful is the gradient of number 1 and the gradient of number 7. Because the algorithm is like, is it a 1 or is it a 7? See, because it looks like a 7. So the 2 gradients are that, because it's a bit undecided. If you go to the number 8, then the rank is 3. And then with my student, we were like, well, number 3, 8 could be a 3, or could be perhaps a 5. So it has, and we look, and the gradients are really the 3, 5, and 8. So we find this very fascinating, isn't it? It's very cool. So we are waiting to write a paper when we finally will be able to put some, you know, geometry, but it is my fault because at geometry I'm a loss of theorems. I'm trying to do it, but so Cinzia, you'll have your precious coffee pause. We stop for like 5-10 minutes and then we leave this subject, and I'll be available for questions, of course.
Thank you.
We killed everybody. So we resume at 4:50. Ok. Un po' terribile oggi. Oggi mi avete detto che ho dato un po' di matematica e ora vi è arrivata. Forse io stavo bene anche se. Perhaps I should pause the audio. Right? Okay, so there was a little vote here on the on the people. So we're going to have like 15-20 minutes regarding neurogeometry, which is not strictly related to deep learning in the sense that it is a separate subject, but it is somehow connected with what I was saying about sub-Riemannian geometry. So this is, don't worry, it won't be technical, it's only 50 minutes, so it won't kill you. And then after that, we will go to geometric deep learning, which is the deep learning on graphs, okay, which is the next topic, which will occupy part of today and certainly all of next time. And okay, so let me share. Okay, so right. I need some help. Okay, I don't know how to put this away. No, I cannot move it. I am sorry, I cannot move it. How do you move this? Probably you don't, right? Okay, we keep it. All right, so neurogeometry was born by this, well, I mean, there is a long story, but let's say that mathematically, it became more and more interesting with the work by Hoffman, which was actually in Caltech when I was there, but I did not realize such a guy was there at that time. Visual cortex is a contact bundle, which is a very provocative title for a paper, because the visual cortex is a piece of our brain, and the contact bundle is like a sophisticated mathematical concept, so it's very strange. Now, a few years after that, this modeling came David Mumford, that you probably don't know who this guy is, right? This is an algebraic geometer, like a very hardcore algebraic geometer that at some point in his life somehow saw the light and started doing machine learning and vision and stuff like that. So turned completely away from algebraic geometry and studied the elastica curve, which I'm not sure I will be able to say a lot, but the elastica curve, according to Mumford, is what our brain uses to reconstruct borders. So if you have occluded borders, we have a way to reconstruct them. According to Mumford, is through this elastica. The elastica curve was also studied by Euler, so it's a very old curve. And I'm saying that these are the two pioneering people putting together mathematics and mathematical models of the visual cortex. And then more recently, Petitot in 1999, and later on Citti, which is my esteemed colleague from Bologna and friend, went a step more and tried to give really hands-on model. And I owe to Giovanna Citti everything I know, because she was the one explaining it, because you need somebody to help you. So, because you cannot do this by yourself. This is how I feel about this. For deep learning, I owe you to Stefano Soatto at UCLA for the neurogeometry to Giovanna. Now let us be, so you were scared to see here, it's only pictures and very relaxing, right? So how does it work in our brain? So in our brain, we have simple and complex cells, and somehow these cortical cells behave like filters. So they're able to detect their directions. So if you remember my previous lectures, right? If you browse through the slides, I was making a lot of noise regarding filters, right? I was saying, oh, you know, it's like you slide over an image and then the filter is learned by the algorithm. And if you look at the filters, it will show directions, right? It will show. And that's actually what happens in our brain. So we have cortical simple cells that somehow encode the directions. And these will highlight these cells whenever in an image we encounter that direction. So it really works, but is it okay? You guys are still with me because I hear all this noise. Perhaps yes. Okay, so in this image is a very, like what can I say? It's a very schematic image. So the visual cortex is represented by this, you know, parallelepiped, this slice, right? You have to know that that's very inaccurate because the visual cortex of a human being is like a sheet that sits here, so it is curved like that. Is roughly a little smaller than my hands, and it is like that. That is behind in our brain. But you imagine that you flatten it, okay? You just flatten it, that is like a sheet. And in this sheet, there are these cells. An hypercolumn is like a section of this visual cortex. And in an hypercolumn, there are all the directions. So when I look at an image, every hypercolumn, somehow you have to morally think of it as a pixel, I mean a little area around the pixel, and the hypercolumn will light the direction that I see, right? So this thing here is a hypercolumn, and see that I see a curve with this direction, and it highlights that direction. So it will fire, that neuron will say, yes, yes, it is that direction. And the other will stay silent. So it's like that, it's really like that. So my image is projected first to the retina of my eye, and then from the retina is projected on the visual cortex. And it is called the retinotopic map because it is really one-to-one map. And then there are these hypercolumns because the retina is like a sheet of paper. The visual cortex is a thick, and then it has all these activating directions at each point. Okay. So this is now this is another model. See, as you can see, it is a very schematic. You realize that the actual cortex is very different, right? It's all wrinkly and so on, but here we have, and then it has right and left because there is a right and left activation. So it will activate the direction, what your right and your left eye, and thank God they are synchronized, so they put the information together. But even just one eye, you can see a direction. That is important. And there is about 18 to 20 columns for all the orientation. So it is very good. And they're about 1 millimeter square. So meaning that you look at 1 millimeter to detect, because you can't look at a point. A point has no direction. You need to look at a neighborhood, 1 millimeter. So we are very accurate, right? I mean, we are able to detect curves in the range of 1 millimeter. This is. And this is, again, I took it from the net. It will show you a little more these orientation columns. That is very, I mean, this image to show to you that is very complicated. I don't even know what this really means, in the sense that there are all of these directions Now there is this thing, pinwheel. I'm just warning you that there is a lot of literature on these pinwheels. I spoke with a doctor. They say they don't even know if they exist. Because if you look at the images of the visual cortex, which are obtained in the worst possible way, meaning that animals are hurt in order to detect, yeah, how you do this, obviously, right? You have electrode and the animal sees a direction and the neuron will fire, right? So you have essentially to kill a cat or a monkey or whatever to get all of this information. It's very terrible. But there are some areas in which all direction concur, and they call it pinwheel. It is very strange. I don't think this is worth discussing, but I'm just saying that some people, I spoke with Giovanna about them, she's convinced they exist. I am not very much convinced. So they be like points where you don't know which direction is lighting. Now, let me try to model it with the mathematics. So depending on your background, you were very worried, but this is like a very simple map. You have the plane and you have a circle and you project it to the plane. So this is exactly what we were seeing before, right? So R2 times S1 is your visual cortex because it's like a plane, but on the point of the plane, you have all the angles, right? Of course, this is false because the circle has infinite angles. We don't. We have only some angles, right? But it is approximated. So in your thick sheet, which is your visual cortex, at the point, there are up over it all the directions. And then they project on R2, which is the image. How do they project? They highlight that border. So this is so R2 times S1 is called a bundle on R2. It's a name, but it is that map. It's not a very, except that there is a lot of research on the bundles. That is the point. And this is a very interesting picture, which I really like. So this picture is done, what can I say? There are volunteers, human volunteers. So I'm giving you this direction. See, there is this horizontal direction. And then I'm giving you this direction, and this direction, right? Now, see that a human being, if you give me, perhaps I could try to draw on this. Let's see if I can. Perhaps I cannot. No, it won't. What did I do? Okay. I am sorry about that. Okay. So I'm trying to say that if I give you these two directions, you can imagine a curve joining them, right? But if I give you these two, you don't complete, right? So it shows to you the dotted ones is that human beings will not say there is a line. You don't say there is a strange line going around. You tend to complete when things make sense, right? If they're like that, what curve is that? There's no curve there, right? So human volunteers were asked to complete, and they completed those. These are the highest. Now it is unfortunately hidden by the banner. There is this completion going on. Now, we have an S1 fiber bundle. At each point of the cortex, we have an information. XY is the information on the point on the image, which is mapped in the retina, which is mapped into the cortex, so the point of the image. And then not only the point, but the orientation of the edge. Okay? So you're thinking, you're looking at an image, there is something, perhaps it won't light, perhaps, but there could be the information about the direction. And then there is also the hypercomplex cell. So the simple cell will give you the direction, but there is also cells that give you the curvature. Now, what is interesting is that if you remember, that was the first time we met, I was showing you the Fei Li course, where we had this, we had the network going in real time, right? And they were showing us the filters. So the first filters look like directions, but if you look at more complex filters, they look like little hooks. So it happens in our brain. The simple cells give us direction. The more complex cell will give us curvature, more elaborate features. One thing I have to warn you, we are talking about image recognition without us thinking. So we recognize direction, but it's not what can I say, an awareness. So it's not me thinking, oh, look at that, I see a straight line. No, my eye will see a straight line without my superior thinking, right? Even an animal, very primitive, without thinking, would recognize a straight line. So I'm saying that there are more a complex human thinking regarding images that we are not talking about, okay? So we're talking just about the cortex that recognizes directions with no further reasoning of our brain, okay? Because there are more complex behavior which I don't talk about. Okay, so what is geodesic and Riemannian geometry? This is the part you will find a little boring if you are not a passionate geometer like myself. So geodesic will will allow you to measure the shortest path between 2 points, okay? For example, if we are in the three-dimensional space like we are in this room, it's a straight line. I go between me and you, there is a straight line. But what if we are on a sphere, right? So a geodesic shortest path on a sphere cannot be a straight line because evidently it's on a sphere. But you can prove that it is a line of a maximal circle around. And this is interesting because when you go from here to Los Angeles, you go through the pole, right? Because that's a geodesic with the airplane. You don't go around, you just go through the pole. So it is, so we know this is, now, this is the equation that of the geodesics. So if x lambda is the coordinate of the curve, right? This is the strange equation. What are these gamma? These are the Christoffel symbols. You ever heard of them? No? Oh. Ah. Poor Christoffel. So if you're having a metric, for example, the Fisher, there was the hope of a metric. These symbols are coming spontaneously out of this metric. Okay, I don't want in the torsion-free case, which is the case you like. I'm just saying that if you are in the space Rn, then this gamma is 0. So the geodesic equation is twice the derivative of x is 0. Yes, it's a straight line, right? The straight line is a line with no acceleration. I go linearly from E to U. If I go with some curvature, I need this symbol. Okay, there is a ample theory about that. Okay, this is shortest path and so on. This is something I just said. Now, unfortunately, this is an example of a bicycle path. It's illustrating the concept of sub-Riemannian metric. So I don't want to put equations, I don't want to study the general theory, but if I have a bicycle and I want to connect the 2 points, I may not be able, with the shortest path, to go with a straight line. I do an example to you. Suppose I am here on my bicycle and I want to connect this point to this point. Clearly, the shortest path is this, right, with the bicycle, because the bicycle has what is called a differential constraint. So my bicycle is not forced on a path like a train. A train, you go on tracks. No. But the bicycle has a constraint due to the fact that the wheel turns, I mean, you cannot do 180 degrees on the wheel, right? So in order for me to go with the bicycle from here to 1 meter there, I have to go and then turn and go back, right? So I'm trying to say that when you have a sub-Riemannian metric posing constraints on your tangent to the curve, to your tangent space, then it's not a straight line. Even if you are in Euclidean space, for example, the plane, it's not a straight line necessarily. Perhaps sometimes it is straight line, but not necessarily a straight line going from A to B. Okay. As it turns out, the plane, which is the plane of the image, the plane of our retina, the plane of our V1, is subject to a differential constraint, exactly as a bicycle. What is it? It is the direction of the tangent to the contour. And the geometry that you get is the geometry of the bicycle path. That is the research I'm doing now. I find it very funny with my students. One is a doctor. So that's an example of, I did the example of the bicycle. This is example of a robotic arm. Evidently, the robotic arm is having a constraint that allow to move only some directions, exactly like the bicycle in some sense. And this gives me the opportunity to say that this beautiful geometric and mathematical subject was discovered by engineers because they had this concrete problem, right? While mathematicians were like, oh, we don't care, robotic arm, why should we care, right? This is the attitude, geometric deep learning, why should I care? This is the typical aristocracy thinking. Okay, so you can have a distribution. I will go very fast because we talked about distributions before. So I can, each point, I specify a subspace, for example, a line or a plane, exactly like we did for the fish. It's the same idea. And here is very good because you can see in this picture what I was trying to express to you. So if you have a vector field, so you have arrows, sometimes there is a submanifold. For example, there is not necessarily though. If you give me a vector at each point, there is no reason why there is a curve through it. Okay, so this is like a Frobenius theorem helps. And okay, so in sub, unfortunately, this is the, so if you look at this picture here on the right, you want to like get more into this subject. So XY is the point on the image. And then you think of lifting it and you have a point on R2 and then the angle. So you see the angle as a third coordinate in your system. Right? So you have a curve, curved contour downstairs, and then you have a lift of the curve upstairs that at each point, see there is the point of the image, the point upstairs, and this distance is the angle. So it's the angle thought as the z-axis. It's not z-axis, it's theta. Okay. So that's a pictorial way of representing R2 times S1, right? You think of the angle as a Z. Okay, so this is. And you think of the orientation activation column. See, this is the hypercolumnar orientation detection. And okay, this is mathematics. You can look at it. There is this mechanism that I wrote in my paper with which you detect the direction. You detect it when it aligns at the most with the vector fields. So whenever the image, so R represents your image. You compute the gradient, right? Whenever the gradient aligns with the vector field, that's a direction. So because you have a contour, right? For example, you have a contour like this. You compute the gradient of from you know, your course of calculus a long time ago. You know that the gradient is orthogonal to the tangent to the curve, right? So if you align a vector field with a gradient, meaning it is the maximum of the scalar product, you have that, that is the direction. Well, it's orthogonal, who cares? It's whatever you see, right? You get the direction. So this is a way to detect the orientation. And see, we do this example because I really like it. So your image Rx is exaggerated, right? You have dark and white, so the contour is very clear, right? And now if you play this mechanism, you see that whenever you take pi over 4, for example, it's pi over 4, it highlights this and that, right? The lowest, the highest, whenever it's like the two directions are pi over 4. And here when you do 3 pi over 4, this is the two directions, the two gradients. Okay, so this is to show that it really gives that. Okay, I don't want to speak about the lifts. Now, for those people that know sub-Riemannian metric, which is not you guys, but perhaps somebody there is a mechanism to compute the geodesics shortest path in a sub-Riemannian metric via the Hamilton equations. And that is what I did with my students. And we discovered, like Chitti and Petitot, they do that also, but they do it with analytic methods. We do it with geometry, that the geodesics are really the path followed by the human brain in reconstruct the image. So this is my last, okay, these are the sub-Riemannian geodesics. So what we discover by plotting our geodesics is that we reproduce exactly the AS fields. You remember these fields where you connect? So we obstruct the image and we're able to reconstruct the borders with the occluded image, exactly as the experiments for the so we have to publish this paper. It's almost ready. I promise I will give it to you when it is ready. So are these questions? I wanted to spend some time on this because it's my current research interest, and I'm glad that somebody got interested into it. But are there questions on this from here or the audience? We go back to the deep learning, I promise. So this was a little bit of a detour. So. Yes. Yes, but in this, exactly, you are correct. So if you read my paper with Petkovic, with in Mainz, we look just at the low visual system. We don't look at the cortex. But in my new paper with Petkovic, we look at just at the cortex. So we go one, and then we should put it together, but Janko is very busy doing other things. So. Okay, so it was boring, but it was short. Okay, so let me go. Any questions from the audience? I want to go back to the deep learning. I will start because I don't want to go until 6 because last time was an error to go for too long. You guys have questions? No questions? Okay, so we're ready for the fun part. I don't know, I have fun in anything, but okay. Sure, audience, you have no questions? Audience is asleep. Right. So now we go to geometry deep learning. So we spoke about deep learning. So I put here the references. There is this beautiful course by Leskovec. So there is a Fei Li in Stanford. She's doing deep learning. And then there is Leskovec, also in Stanford, doing graph neural network. I like what he does. He's very clear, but I must say that he's biased because he really like what is called random walks on graphs. which is interesting to some people, but not to me. So he will do everything like a random walk, but no, random walks, okay, fine, it's interesting. But, so the course is a little biased on Leskovec taste, but okay. And then there is the other reference by Bronstein. Bronstein is the initiator of this subject. He got an ERC grant called Geometric Deep Learning, where he was exploring spectral methods. And he says, going beyond Euclidean data, as I said to you before, that's really inaccurate because graphs are Euclidean. Any graph can be embedded in Euclidean space. So he calls them not Euclidean, but I don't know, he's an engineer. Let's forgive him, right? I'm also an engineer. I'm full of forgiveness for such people. All right. So let me very quickly remind you what we're talking about. We have in deep learning, we have a score function, we have a loss function, we have an optimizer, stochastic gradient descent, whatever, right? In geometric deep learning, it is the same. We have a score, we have a loss, we have an optimizer, and we do an optimization, okay? Same idea through epochs, learning rate, and so on. What is the difference? The very important difference is that you have graphs. So your data is organized in a graph. Hence, instead of having a score function on an image, which is very simple, right? Because you multiply weights, you do convolution, whatever you do, it's an image is a vector. So it is very simple to discuss. Here you have a graph. So things won't be so easy. So there is no vector representing your data. No. It's a graph, it's more complicated, okay? So what I'm trying to say is that deep learning is an algorithm where you have a certain thing going on, score, loss, optimizer, blah, blah, blah. Those are the same. The thing that changes is how to compute the score. That's the thing, how to get the score. No easy fact. Okay, so the real problem is the convolution on graphs. Why? The reason is that if you have an image, you do convolution by sliding a matrix, right? But with a graph, you can't do it. Why? Because in a graph, you may have, for example, a node connected with 10 nodes, and then the other node is connected with 2 nodes. So what is going to be your filter? It makes no sense, right? That's a big problem. Okay. But it has the advantage that if you have a graph, you can consider data sets that are way more complicated than images, right? As I said, I have a medical data set. Right now, I'm working on medical data sets. They're all graphs and no images. Moreover, you can also work on 3D images because a 3D image is better if you cover it with a mesh, right? So let me tell you this very, what can I say, very inaccurately. So let me make this statement. If you look at Bronstein and spectral methods, they work very well on 3D images. That is, you have a body, for example, the industry of movies, they do that, they cover it with a mesh, and you want to reconstruct the movement, for example. That works really great with spectral methods. I will try to explain why in next time. But if you work like me on medical data sets, in spectral methods are a lot of complication and are not worth it. So it depends on what you want to do. I don't know what the database, what database are you looking at? Of a given object, yes. I am afraid to say perhaps the spectral methods will work. I don't know. How about yourself? What is data sets? Then spectral methods. They work better. Yes. Okay, but this helps me because next time I know where I should focus. Dobbiamo andare via? Perhaps I stop in 15 minutes. Eh? What is the time? 5:30. Let me keep my myself. No, because last time we were late and the people were not happy, so they're trying to give us a hint that we. It's early. I know. We will, but we will stop like in 20 minutes, no more. Perfect. Okay. So go. Mhm.
And this is like connecting some areas.
This is Lechkovec random walks, isn't it? Yes, yes, go. Go ahead. It looks to me really like something Lechkovec does in detail, moving along a graph, right? Yes. Yes, yes. Yes, yes. I see. Is it related with the piano problem? No, you don't. Okay. Configurations of how to move a piano around. No, it's not that. Okay. Take a look at Lechkovec. I'm not interested in what he does. I am sorry, so I will not address this question. But okay, as I'm going to say, these lectures will be really biased on some type of problems that I'm interested in. But graphs are really very, very flexible. They get anything into them. So I'm choosing a direction which I'm interested in, but you are right. You can use them for a lot more than deep learning on images. Yes. Okay, so do ask the same question in a short while, okay? Let me show you what are the possibilities, and then we reason again on what you're asking, okay? So the typical graph that is interesting is a social network graph. As I said, you can think of a user as a node, and then you can have edge if I'm friend with. Notice the possibilities are many. For example, this shows to you that, okay, there is a very simple graph that nodes are users and we connect if there is friendship. Very simple. But no, with the graph neural network, you can be more complicated. There could be different nodes and different edges. For example, in this social network, you have that there are users. For example, these are people, but also companies, Spotify, oops, sorry, did I do? Spotify, Netflix, these are not users, these are companies, and you can have different type of edges. So I'm telling you that very soon the possibilities are multiplying exponentially. And I think is not useful for me. So I prefer to tell you what I know instead of going through all the possibilities because I don't know. It seems more confusing to me that time. Okay. So what are these? So first of all, I'm looking only at supervised classification problems, not because they're most important, it's because it's what I do. There is, no, this is by the way, this is Petkovic. He's probably calling me for the paper. All right. So there are many interesting problems unsupervised, but we don't touch them. Okay, it is possible. So what are the possibilities? You can have many graphs, okay, and each graph can have a label. So for example, my student did a project where you had proteins as graphs. So you give me a protein, it is encoded as a graph. There is a database regarding proteins, And then it has a label whether or not it is an enzyme. So 0, it is an enzyme, 1, it is not, or vice versa, who knows, right? And then you train your algorithm to recognize the features that make a protein enzyme or not. And then you give another protein, it will tell you, yes, it is, or no, it is not, okay? So this is a very similar to deep learning on images, right? You give a label and you predict the label, very simple. There is another extreme to this situation where you have one graph, and this is closer to what you're asking. Let's try to figure out, okay? So you have just one graph, and you want to classify nodes or edges, perhaps both, but let's not worry, let's keep it simple. So, for example, you want you label the nodes of your social network, say a node is labeled 0 if it is a common person, is labeled 1 if it is a celebrity. So you run your algorithm on the graph with the labels that you know, and then you suddenly say, oh, I have a node that is not labeled, is it a celebrity, yes or no? It will give you the answer. Clearly, as I said you before, it's not very smart, this question, because obviously a celebrity will have more links than a normal person. But this is the idea, okay? So nodes may come with features. What is features? Is that I am a node, for example, my feature could be, if I'm looking at a medical record, say, oh, Fiorese is this height, this weight, has or has not diabetes, has this chronic illness. So I come as a node, but instead of having a label, I have a whole array of labels. And you are another node, we are both in the same hospital, and you have an array of labels too, because your parameters are monitored in some sense, right? And so we connect patients that have similarities. For example, we may connect patients that, for example, are related, like parents, children, brothers, because this is sharing a common, or perhaps if we're interested in some illness that depend on the age, we relate people that are near of age, and then we run the algorithm, and the purpose is to discover your feature. So the algorithm has never seen you as a node, doesn't know your features, but because of your connections, so knows the features of your cousin, knows the feature of somebody close to you in age, and can predict your features. So you see the point. So when you say predict a graph, it can predict an array of features. If it has a further organization, I don't know, okay? Because everything I'm telling you now, it is encoded in PyTorch. So you can really, so this thing of enzyme, not enzyme, it is in PyTorch, you can program. It is actually called PyGeometric, but it is there. And so it's really like MNIST and CIFAR, there are benchmark data sets. One is called the Zachary Karatik Lab that we're going to discuss. The other one is called the Core dataset, and they are available exactly as MNIST and CIFAR, and you can play with them. These two datasets in particular will not help you because it will predict a label. So they're toy things, right? So I don't know, does it answer partially? Some. The truth is that I don't know, because I'm not interested in producing a graph. Okay. So as far as we are concerned, for the sake of being simple, we will work only to the prediction of a node. So the questions I will illustrate to you is that I give you a graph, some nodes are labeled, some nodes are not labeled, try to infer the labeling of a node. Okay, so one graph, node labeling. With a little effort, you can play the game of edge labeling, similar. But you can do even more sophisticated stuff. For example, you can predict whether or not there is a link between us. Okay, this is more like is tricky because when you run the algorithm, in that case, you don't have the graph, right? Because you're trying to predict. So it is a bit tricky now. But we keep it simple because I think it's already complicated in this simple case. Then you add layers to your study if you need. Okay. Okay, so we go. So this is a picture taken from Leskovec. Here is the typical problem. You have this graph. The graph is the same. You don't change the graph. Same number of vertices, same edges between them. And then you see the gray one, you don't know the label. You want to discover the labels of that. Okay. Remember, the game is always the same. You have the score, you have the loss, you play with stochastic gradient or variation of. That's it. How do you get the score? Because the score is convolution. How do you do that? That is the point. Now, one thing I want to say before we go on is that a very important difference between deep learning and geometric deep learning is the quality of data. Because one thing I didn't stress in deep learning is that you really need a lot of data to make it work. So when you're trying to train a neural network, I don't know if you tried, but you need the thousands of data, thousands of images in order for your algorithm to be effective, right? That's the point. With geometric, no, it's not like that. You can have a very few data and you can still get meaningful predictions. This is great for medical because in the medical realm, it's impossible to have 1,000 and 1,000 of data. Perhaps you have a few hundreds if you're lucky. Perfect. That is the thing. Okay. So when you're looking at a graph neural network, you have the following steps. Okay. You have a step called encoding that you don't. So encoding and decoding are new. They're not in deep learning. Loss and optimizer, identical. So the encoding realizes a low-dimensional embedding of the graph. So you have your graph. Your graph comes, I will show it to you in certain nodes whatsoever. You try to associate to each edge and vertex a low dimension information. Okay, we will see what it is. And then you do a decoding with which you compute a score. I know it's very obscure, but let me try to show to you really what happens because, okay. So you take a node is associating to a vector. The vector encodes its feature representation. Then once you have this vector obtained in some mysterious way, which I will explain because not simple at all, how you produce this vector. With the decoder, you give me the classes, the scores. So just to have a feeling where we're going. The encoder morally is like when you were doing the convolutional filters, right? In the deep learning, you have a set of convolutional filters. Then you reach something and you straightening and you do a linear layer and you obtain the classes, 10 classes. Here is the same. With the encoder, you do the convolutions, which are a mess. Great. Then the decoder will give you a linear time this mess, I will explain, will produce a vector with the classes. Because a node as a label, perhaps is a node, I don't know, is a label between 0 and 3, will give you a number between 0 and 3. Okay, or 0, 1, celebrity, not celebrity. Okay, now I really believe that the most important thing is to understand what we're doing. So I give you an example because I don't think that we can understand without an example. This is my feeling. And keep very, what can I say, very close to you, this reference, Kip van Welling. I know Max Welling, he was a professor at Amsterdam, and now Microsoft has bought him. it is so sad because my friend Stefano Soato at UCLA, Amazon bought him. And now you're probably thinking, I want to be bought. But no, research is not for sale. Max, what are you doing? I told him that. I said it's okay. Sad, but inevitable. This is why the research is not going as it should in this, because if companies are buying these people, then you see what is happening. They take them away from research, right? Okay, so what is Zachary Karate Club? Okay, so this is a karate club studied by this researcher Zachary. I think it was in the 70s or in the 80s. So way, you never heard of this, have you, Zachary? No, okay. So there was this club. It was really karate. So it was, I think, in San Francisco, and there were people going to this club to play karate, right? I mean, it was a cool thing. I think it was, so I think it's 34 nodes. And each node had the label 0, 1, 2, 3. And so it is interesting because these nodes are connected because these people form the groups, okay? And these groups, this researcher, Zachary, for me, it's not, so it is coming from a sociology study, this and as you can see, these groups somehow, you see, are connected, but they also share, so the color represents the label that is assigned. And the different color represented their opinion on how much the monthly cost of the karate club should be. So they were very passionate about that. I am told that in the end they split. They couldn't agree on the tuition of the club. But it doesn't matter. So there is, though this example shows to you that there is a link linking different nodes, and there is a coloring. In principle, there is no relation between coloring and links. So if you have your own database, you can do what you want, the label and do links. But the truth is that if the labeling is not matching the links, there is no hope that there is a prediction, right? Because if I'm in a hospital and I link random people, how can I make a prediction if I'm linked to, I don't know, like a black man of 34 years old that doesn't have any of my illness, right? I mean, this makes no sense. So what I'm trying to say is that look very carefully at this picture of the graph, because it shows to you that the only hope a thing can work is that clusters are colored the same, right? Otherwise, so don't put too much hope in your, for example, right now I'm working with Ferdinando, the guy that you met last time, and we're trying to cluster neurons in the human spine. Okay, so human spine as neurons. So there are fibers, human, la colonna vertebrale, human. And so the point is that when you put pain, you activate these neurons. When you give medicine, neurons activate, and they activate in pattern. So we're trying to see if this pattern corresponds to the neurons that are linked. So the graph is given to us to the structure, the physiological structure. But if there is no structure, then there is no hope you can classify, right? So we're trying to predict what neurons will be activated by certain medicine. So the first thing that you do an encoding function sending each node of the graph into the plane. So you see A is your graph, B is the encoding. As you could see from the encoding, there is these clusters. Remember, in the end, we're going to do a linear. In the linear is this thing with the hyperplane, right? So the encoding must be in such a way that what you obtain can be linearly separated. Otherwise, you cannot play the game, right? So I'm trying to warn you because I've been facing these difficulties, right? If your encoding is a mess and doesn't linearly separate, you are done. That's finished. You can't do anything. Okay, so let us see how you implement in Colab this graph neural network. So the encoder consists in a series of convolutions. What is this convolution? We have not explained yet, okay? We wait, but it is the analogous of the convolution for images on graphs. So you take your 34 nodes, you do a conv, so it gives you a 4 and then 4, 4, 4, 2. In the end, you produce from your R34. So each node, I am sorry, I didn't explain myself. I am very bad in explaining. So each vertex, you think it as 1, 0, 0, 0, 0. Second vertex, 0, 1. So it's the canonical basis of R34. Okay. So each node occupies a dimension in R34. And then you squeeze it until you project it on R2, a plane. Okay, that's the game. Now, exactly, see the encoding, so you start from R34 and you squeeze it in R2. And then you have to predict the labels. Here you have the 4 labels, you go from R2 to R4. If you add 6 labels, R2 to R6. Okay, that is the, notice it is a linear, it is always a linear. So the encoder somehow encodes the information of the nodes into this R2, a point in R2, and then a linear expands it to R4. So I don't know if you are familiar with the encoding, decoding in deep learning, right? That there is, first you go down and then you go up. This is why it is called encoding decoding. If it is Yanko, I will divorce him. Okay. I'm sorry, I have somebody that I have to help and, okay, no, it's not Yanko. All right. So I think we are almost running out of time. I don't have the time to explain the message passing and convolution. So perhaps, so I want to show you why I don't want to explain it to you, because this is the thing I should have to explain. This is the convolution. So no, I'm just telling you that it is a mess and we're going to go into it. But perhaps that's not very smart to do it in the last 10 minutes. So we will do next time. We start from here. If you have sometimes at end, go to the message passing by Welling, Kip, and also the Leskovec. So the next time we start from there, we take half time doing message passing, convolution, and graph attention, which is very important. And then we go to the spectral methods in the last part. That is the plan. Questions? So I wanted to finish 10 minutes earlier because last time they're really mad. Okay, so guys, the few people that resisted up to now, do you guys have questions before they kick us out? I will post these slides on the web so that you can take a look at them before next time, and then the spectral method, I still have to finish them. So happiness. All right. So there is no emotion from our friends. So Thanos, are you alive?
Yes, very much.
Very good, very good. All right, all right. So goodbye to everybody and I will see you, okay? Bye-bye, guys. Bye.
Bye.
Bye-bye, bye-bye.
Thank you, bye.
Ciao.
Bye.